Okay, so we're going to take a look at the natural log, or we're define what a natural logarithm is, which, I mean, at this point in your math journey, you have probably dealt with a log in some capacity, right? And really, they just introduced what a logarithm was, probably in relation with an exponential, right? But now we're going to take a look, and usually the idea came with we have an exponential, right? We define that right in terms of exponential growth, right? And then we define the log kind of like as an inverse because it had to have an inverse because the exponential is 1-to-1. But here we're going to take a different lens to it here. All right. So the kind of motivation here comes from the power rule for antiderivatives. Right. So we know here that we have the power rule. All right. Where previously, we have defined this in your calculus course and probably for all rational numbers, right? Not all real numbers. That's something we'll probably prove here, right? Or in this course we prove, right? So for all rational numbers, this works, right? For 1, 2, 3, right? 0, right? It's just a constant, right? Half, 2/3, -2/3, -3. It really works for all these values except for 1, right? Whether it's rational or irrational, it will never work for this value, n is equal to -1. So we kind of have a gap here in our knowledge, right? There's a gap for this formula, right? In math, right? That we can't use the above formula to do something like this, right? Or written like this, dx over x. So our intent here is to fill this gap, right? Now, we do that by, we're going to define a function in this way. We're going to, capital F is going to be equal to 1 over x dt over t. X must be bigger than 0. Okay? It can't be 0 here. Because of the way it's defined, right? We'll be dividing by 0. And now another thing is why 1, right? We could have, and we'll see, we're going to reference the fundamental theorem of calculus, that that value in the integral could be just some constant a. Right? Now the reason we chose 1, right, is that for this particular value of 1, we get lots of very interesting properties that develop from a. Right? It takes multiplication and makes it into addition. It takes division and turns it into subtraction. Right? So that's the reason for choosing 1 down there. Right? Now you can maybe start thinking, well, that looks like a logarithm type properties, right? And that is correct here, right? In fact, the definition here, we want to define what the natural logarithm is. Right? So here we want to define definition. Okay, so we're going to take a look at the function 1 over t, right? So for each, and actually before we get into the definition here, also one thing to realize from that fundamental theorem of calculus is, right, that it applies here, right? We have a continuous function for x values bigger than 0. That the derivative of this function is equal to 1 over x. Okay. So theoretically, we do have an idea of what this antiderivative is. It has to exist, right? Remember that fundamental theorem of calculus that I applied here. What that's hinting at is that antiderivative exists. I just don't know what it is just yet. So I'm going to put a name to it, right? So I'm going to define the natural logarithm. So here we have a definition. Right? So for each x larger than 0, we define the natural logarithm. Logarithm of x to be the number x dt over t. Okay. All right, so we're defining it here, the logarithm, the natural logarithm, all right, as this here from 1, right, essentially the area under the curve. Right, so if x is bigger than 1, right, it's the area from 1 to that value, right? And based on the order of the limits, right, if it's to the, so a couple things here, let's kind of look at this here. So some properties of this natural logarithm. Again, this is what a natural logarithm is, right? We calculate that integral using numerical integration to find what that value is. It's area under the curve under that integral, right? So if x is between 0 and 1, right, then the natural logarithm is a negative number. All right, and again, it's unbounded, so the closer it gets to 0, the larger and larger that negative value gets, right? Again, never actually taking on the value of 0, right, because x is undefined at 0. But the closer we get, the more unbound the area gets. All right, if x is bigger than 1, then our natural log is bigger than 0. And when x is equal to 1, then we get, again, this is from properties of integrals, right? I think before all these properties were framed in terms of the exponential, right? But now, actually, the understanding of natural logarithm here is through the lens of calculus, right? Where we take an integral across one point, well, there's 0 area there. Right? So now based on kind of these properties here, we can start to see, well, this function is always decreasing, right? But it's never 0, right? As x goes to infinity. So I can think of a couple of limits here, or a couple of properties involving limits that describe our natural logarithm. The limit as x goes to infinity of the natural log of x, right? Now, x never attains, or excuse me, 1 over t, right? This is the 1 over t, never attains the value of 0. There's always some positive value that we're adding on here, right? So the ln value is going to go to infinity as x goes to infinity, right? Very slowly, but it will eventually get there. Now, as x goes to negative, as x goes to 0 on the right, from the right, of ln of x, right? So here, again, notice that it cannot be defined on values that are to the left of 0, because if we try to define it in this way, any kind of neighborhood around 0 on both sides leads to an unbounded integral. So it's just not going to be defined. Right? The values for the natural log, the input of the natural log, must strictly be positive values. Okay? So the values here go to negative infinity. Right? So now we actually have an idea of what the graph of the natural log looks like. Right? I have a point here, right? I know that it crosses when x is 1. I know it's 0. And then as x gets larger in the x direction, it goes to infinity. Now, slowly, but it gets there to infinity. And in the other direction, it goes to negative infinity. Right? Never crossing over to the x-axis because the input is not defined to the left of the origin. Okay, and then this is our graph of the natural log of x. Okay, again, based off of, again, properties that we've derived from calculus. So now we can actually define a a way to take the derivative of the natural log. All right, so the derivative here of my natural log, using the fundamental theorem of calculus, dx of 1 over x dt over t, well, that's just 1 over x, right? And in terms of the chain rule, if this input is some function of x, again, call it u of x, then the derivative of this would be 1 over u, right, this function u of x, times the derivative of whatever that function is. Okay? All right. So now let's go back to some of those properties that I mentioned earlier, like this one here. At least the first one. I'll prove the first one, and then based on the result of the multiplication one, you can probably try to see if you can prove that f of a divided by b on your own there. But here, let's take a look at our first theorem here. Okay, so here we state that if A and B are positive, then ln of AB equals to ln of A plus ln of B. So now here we are going to require some knowledge from some of our Math 1 theorems that we went over, or that you should have gone over in Math 1. And I'll just state them here as I go along so we get an idea here. Now the first one being this, first let's take a look at when I want to prove this here. So let's see here, let's see our proof. Okay, now one thing to realize here is I'm going to start looking at these two functions, the natural log of ax and then the natural log of x, right? Where a is some constant, right? And x is our variable, right? X can be anything. Later, at the end, we're going to let it be b. But we're going to start off by first doing this because I'll take the derivative of each one of these. Okay. Okay, so when I take the derivative, here again, we're going to need a chain rule for this one, right? A is just a constant. So the derivative would be 1 over ax, right? Again, using the chain rule, right? 1 over whatever the input is. Now I'm inside and I take the derivative of the input, which is just a. All right, so this leads me to be 1 over x. Okay. All right. And then this one is a straightforward one, no chain rule needed. We have 1 over x. Okay. All right. So what we notice here is that for both of these functions, they have the same derivative. Now, in Math 1, we had a theorem that stated that if any two functions have the same derivative, that means that they differ by a constant. Oh my God. Okay. Oh my God. Okay. All right. So I want to actually solve for this constant, right? And I can do that by letting x equal to 1. If I let x equal 1, then we get ln of a minus ln of 1 Okay. All right. And then I know from above that I just showed that the natural log of 1 is 0. So we get ln of a to equal to c. Okay? All right. So that means that c is equal to ln of a. So that means going back to my original statement, ln of ax minus ln of x is equal to ln of a, whatever that constant is. And now letting x equal to b, let x equal to b, we get ln of a b minus ln of b to equal to ln of a. All right. And rearranging, bringing the b over to the other side, we get the property that we're familiar with. Ln of a b equal to ln of a plus ln of b. All right, and that proves our statement there. All right, and again, notice you've probably seen this defined, derived in an algebra course using exponentials. Notice there has been no mention of what an exponent here is. Okay, it's strictly based on calculus. All right, now let's look at another property here that we can prove. Here is, all right, so another theorem here. If R is rational, then the natural log of x to the r is equal to r ln of x. All right, and we take the same approach here, right, where we take the derivative of each one of these on the left side and the right side of the integral, excuse me, of the equal sign. So the derivative with respect to x of ln x to the r. Now remember, r is just some rational number, right? So chain rule here is 1 over x to the r minus 1. And then inside, right, derivative of x to the r is r, excuse me, got ahead of myself here. 1 over x to the r, right? Chain rule, leave the inside alone. Now I apply the power rule to the inside. R, x to the r minus 1. Okay, and doing a little simplification here, this reduces to r over x. Okay. And now let's do this with our other function, right? Derivative of r ln of x. All right, now this is a constant, so you can really just, you're not going to be taking the derivative of that. Just take it out of the derivative operator, and then you just get 1 over x times r, which reduces to r over x. And now again, we have the same idea here, right? If those derivatives are equal to each other, that means that the functions themselves must differ by a constant, right? That means that the natural log okay. The natural log of x to the r minus r natural log of x is equal to c. Okay, and what that's going to get us here is that, so now I can solve for c by letting x equal to 1. And we see in both cases, the x is equal to 1. We have natural log of 1. So that means that here we'll get 0 is equal to c, and then we can right away from there jump to our conclusion. If c is 0, then I can rearrange one of the values on the other side of the equal sign, and we have our desired result. X to the r equals to r ln of x. Okay. All right. So now we have just kind of there introduced the natural log in terms of the, excuse me, in terms of that integral, right? And that is exactly what a natural log is. It's just the integral of that function 1 over t. Okay, so now let's take a look at one special derivative here, and then we'll use that as a way to find the integral of a function that we couldn't integrate before. So first, let's start off a couple of examples here. Example here. Find f prime of x if f of x is equal to the natural log of the absolute value of x. Okay. All right. So we'll start off first by, in order to work with anything that has an absolute value, I'd like to drop that absolute value. So the way we do that is by having some kind of piecewise function. So f of x will be equal to ln of x for x bigger than 0, and ln of negative x for x less than 0. All right. Taking the derivative of this function now, right? And again, don't get thrown off by this negative in there. If x is less than 0, x is negative, so negative gives me a positive. So it's still following the domain of my defined natural logarithm function. Okay, now we see what happens here. The top one is straightforward, right? 1 over x for x bigger than 0. For the denominator, using the chain rule, we get 1 over negative x, and then the derivative of negative x is negative 1. So we actually get back 1 over x. Okay, so what does that mean? That means that now I can arrive at this conclusion, right? I found the derivative, right? So that means that I can now define an antiderivative. Right? So what that means is that the integral of 1 over x dx, right, just in general, right, the definite integral. Before we had in terms of the a finite, the indefinite integral. Previously, we defined the definite integral as a number, right, the natural number. But now here, the integral here of 1 over x is the resulting function ln absolute value of x. And again, as always, don't forget the plus c. Okay. All right. Now this allows us to, it allows us more functions to find the integrals of. All right. In particular, I'll do one example here. I can now evaluate this function, right? Tangent of x dx. All right, now previously I did not have this knowledge here. All right, I knew basic integral functions. Really, the only integrals of trig functions I knew were just the, if it was a derivative of sine, cosine, tangent, etc., then I could find the antiderivative if it was that particular function, right? For example, the integral of secant squared was tangent of x, right? And the reason I knew that because the derivative of tangent of x was secant squared. But this does not fall in that category, right? But now what I have is I have more tools, right? I have this natural log derivative, and I also know a u substitution from a previous section. Okay, so let's say I wanted to evaluate this. Okay, all right. Now I'll start by, first I'm going to make the u substitution, that u equal to cosine x. That means that du is going to be negative sine x, or dx, and in other words, negative du, just multiplying by negative here, is sine of x dx. Okay, all right, and now plugging that in, right, I have negative the integral of 1 over u du. Okay, and now it's a basic form, right, or a new basic form, right? That one is the natural log. So we have the integral here becomes negative natural log absolute value of u plus c or negative ln of cosine of x plus c. And again, right, that negative in front, remember from the previous theorem, that's actually an exponent. So it's cosine raised to the negative 1, which is a reciprocal. And the reciprocal function of cosine is the secant of x plus c. All right. And that is how we can now use the definition of the antiderivative of the natural log to find to evaluate new integral functions.